Okay, so you are looking at last class two things, right, the efficiency calculations eta p, right, and then the melting rate. And efficiency calculations we were deriving the heat in anode and cathode, is not it, QC or QA. So, based on the polarity, so we can assume that in the workpiece is a anode or cathode. So, the amount of heat which actually goes in to the workpiece is determined by the polarity, if it is using in straight polarity or reverse polarity. In GMAW process it is both QC plus QA, because whatever heat is generated in the cathode, it is also transferred back to the workpiece. So, if it is electronegative. Okay. So, in GMAW process it is addition of both QC and QA, that is why in GMAW process the efficiency is much higher, right. And then the efficiency is also determined by this term. So, this is the term which determines the heat generation in the arc column, is not it. So, when you are looking at in a QA, for example, so this we were deriving the equation is the heat generation in the anode plus I plus the amount of heat transferred from the arc column to the anode, is not it. So, that not all the heat is transferred, only fraction is transferred based on the heat radiation, conduction, convection from the arc to the anode. Okay. So, that is again determined by the fraction and then V column and times I. And how do you calculate this value? So, V column I, and this can be transferred into I times V equal to V is IR, is not it, and then it becomes I square R. How do you calculate R? So, this is electrical resistivity of an arc. We derived an equation for that, is not it, right. So, we derived an equation to calculate the electrical resistivity of an arc. So, that we can use it to calculate the resistivity of an arc, so that we can calculate the heat generation in the arc. It is clear, that is why we derived that equation to calculate this term. So, again, so the efficiency is also determined by how much heat is transferred from the arc column to the anode if it is QA, right, in the workpiece. And then, so in anode you also add the heat from the work function, because work function is spent in cathode and that is gained in anode when the electron reach anode, right. So, this is the work function of cathode times again current plus the electrons also get heated up and they also carry heat to the anode, because when they enter the arc column they get heated up from the temperature of the cathode to the arc column temperature. So, we can measure that, is not it, from the Boltzmann, and then this is T column minus T anode, this is T column arc column minus cathode, because electron is coming from cathode only, right, divided by E times I, is not it. So, this is all plus term in anode, that is why the temperature is always higher in anode, right. In the cathode we have minus terms where the work function is spent. Similarly, electrons also gets the absorbed heat while the electron gets heated up to the arc column temperature. So, now this is the heat available in anode and the cathode, right. So, now with this equation, so this is the main heat is available for droplet to melt, right. Suppose if you are making your consumer electrode as an anode, the heat available to melt is this, is not it. So, that is what heat is there in the anode, and then we also have a additional heat that is coming from the resistance heating. Okay. So, this is the main heat available in the anode for droplet to form. Okay. So, that is the heat is coming from the arc for the melting of the electrode, plus we also generate heat in the anode if the consumable electrode is anode. So, that is the Joule heating, that than the resistivity of the wire, is not it, okay. And then equation is rho L by pi r square, very good. And then so this takes care of R. So what is the equation to calculate the heat from the resistance? So I square R, isn't it? So that is the heat generated by resistance, by Joule heating at the wire. And what is L here? So L is here is stick out length. Suppose if you have a contact tip, okay, and then wire will be sticking out, the consumable wire, and then it will form the arc, the base material. The distance between the contact tip to the arc, so this is the stick out length generally we define, and this is very crucial parameter in JMAW. So when you are setting it up, that is what we saw in the previous class also. And these two are the heat gain. So this heat generated, if your consumable electrode is anode, so this is the heat generated and can be spent for melting. And then so we have additional two terms. The first term is latent heat of melting. This can be exothermic or endothermic based on the system. Okay, most of the time the heat should be supplied for melting. Okay, so latent heat, which is H, so and then so once you melt it, droplet will not be in same temperature, melting temperature. It will be heated up to a temperature at which it can be transferred. Okay, so from the melting temperature it should be heated to a droplet temperature. It may not be at the melting point. So it has to be heated up in order to separate, isn't it? We will see in subsequent classes, in this class itself in the later stages. So what will be the temperature of the droplet? Because if it is a melting point, just exactly melting point, and the droplet the surface tension will be very high, isn't it? And you will also have, if an instability, the droplet cannot be detached, we can also solidify, isn't it? So the droplet should be superheated, then only it can detach. So the moment your droplet forms, it is exposed to the arc, it is also heated up, isn't it? So the additional term which actually consumes during melting process is to increase the droplet temperature from the melting point to the droplet temperature, isn't it? So that term is, say for example, the heat needed to increase the temperature, right. So that is a function of specific heat capacity times temperature of the droplet when it is getting detached and the melting point, isn't it? It is simple. So by balancing these four, we can calculate the melting rate, isn't it? So this is the entire heat balance used for melting. There is no other heat, there is no other consumption, only these four. So latent heat can be positive or negative. So when during melting, some system may send heat. Okay, so when some system melts, it can be exothermic. So then this term becomes positive. System tend to melt. In most of the cases, we supply heat for melting, so it becomes endothermic. So either it can be positive or negative. So by adding all these four, so we can calculate the melting rate, right. So in these four equations, most of them are material specific and then process specific. That is why we looked at it. So for example, in this case, the only variation independently we can vary respect to a material is current and then stick out length. For a given diameter of the wire, these two L and I square you can vary. Okay, so this is a material function, again this is the material function, isn't it? And in this QA term, so this is material function, isn't it? Of course, if you take I out, this becomes material function, and this is process specific. If you fix a process and a shielding gas, right, this is fixed. and in this case, and V A is the voltage in the anode drop zone, right. Again this is a process specific. So, the main variable you hear again I, and all other things are either material dependent or process dependent. So, now for a given material, for a given process condition includes shielding gas. Okay. So, the important variables what you see over here which controls the melting rate are the current, stick out length for a given diameter. Okay. So, these two mainly, the current and the stick out length, you can independently vary for a given process for a given material of a given diameter. Suppose if I give you 1.2 mm diameter carbon steel and I ask you to weld using GMAW using argon as a shielding gas. So, all other things are fixed. Okay. Only two parameters you can vary is current and stick out length, right, to change the melting rate. So, the most of the welding process specifications when you are generating for a given diameter wire for a given process, we generate as a function of these two parameters, stick out length and current. It is clear, because these two are the independent parameter we can vary for all the process and the material specifications. It is clear. So, we derived the melting rate equation kilograms per second. So, that is the equation what you get. So, then we can do a balance when identified the equations, right. So, this is what I have written here. So, in this case QA and QC. So, what polarity will be more advantageous if you want to melt more? Which polarity is better? Reverse polarity. So, making consumable anode. Why? All the positive terms. So, heat is high in the anode. So, if you want to melt more, if you want to deposit more, that means that you need to have a high heat. QA must be used because anode is where the heat is maximum because all the positive terms. So, if you want to melt more volume per time, per unit time, you can make your consumable electrode as an anode. That means that reverse polarity in DC. So, that means that you can increase the melting rate. So, when you are doing a welding and the polarity selection, it is not just like that you do a direct current DC electrode positive or electrode negative. So, we need to take into all the physics. So, that is a lesson. Okay. So, it is not like an all thumb rule or just rule of mixture or just like that you okay weld with argon with a straight polarity and start depositing, because you are changing the physics entirely. So, this is extremely important to understand what these polarity mean and how they can interfere with varying levels. So, in a conventional welding process, it can considerably change the melting rate because heat in the anode is changed. If you are changing from anode into cathode, if you are making from electrode the reverse polarity into straight polarity, so you have less heat in the consumable. So, your melting rate decreases if you are making it as a cathode, right. So, we can derive a very simple equation by looking at the heat balance. So, QA, if a consumable is being an anode, which is the most likely situation, and if you want to increase the productivity, you always make your consumable electrode as an anode, so that all positive terms will increase the melting rate. And this term is the resistive heating term, and L is the stick out length, and the R is the diameter of the filler or radius of the filler, right. And using that we can derive a simple equation, because there is I term in the QA term and I square term in the Joule heating term, and A and B is a constant for a given material and the given process conditions. So, we can take the A and B out because they are constant. So, ultimately you end up getting an equation like MAI and then plus B Li square by pi r square, and A and B we can calculate for a given process condition for a given material. So, for example, I just calculated a few A and B. So, in this case, so A and B for 1.2 mm plain carbon steel, which is most commonly used filler wire. For argon atmosphere. Shielding gas is an argon, and if you use argon shielding gas for 1.2 mm plain carbon steel, everything is fixed. So, process is fixed, GMAW, argon atmosphere. So, the R column heat generation is fixed, right. And then, so what are the varying, now the A is fixed and B is fixed, only two parameters you can vary, they are stick out length, current, to change the melting rate, right. Similarly for aluminum, so this term really negligible, so this goes away, so B goes away. So, you can simply assume that AI plus Li square by pi r square, right. So, this is against 1.2 mm. So, in this case the B is negligible. So, once you know A and B for a given stick out length and current, because anyway, so once you know A and B, so you can calculate the melting rate, which is alpha I and then plus beta I Li square by pi r square. So, A and B is material and composition specific. So, that is what you need to see here, right. So, once we know these, so now we can calculate the melting rate accurately, and then the beauty of this is it is very important to calculate the melting rate for a given wire to keep the wire arc, the arc length constant. Suppose if you are doing it in a constant voltage welding, the arc length should be constant. That means that whatever amount you melt, it should also feed, right. So, suppose if you are melting and you want to keep the arc length constant, so suppose this is my wire and then I am making an arc and this is constantly melt and then transfers to the workpiece. Now, if you want to have a constant arc length, the wire feed rate should be same as the melting rate, right. Suppose if you want to maintain the arc length constant, we will have to see that the arc length kept constant by constantly feeding same wire feed rate as the melting rate, otherwise your arc length will change, your voltage will change, is not it. So, now in order to keep the arc length constant, and the power source would be capable of calculating the melting rate for a given wire composition in the process. So, that is where it goes into the microprocessor control system in GMAW. So, suppose if the wire feed rate should be kept constant, that means that the system, the power source should be capable of calculating the melting rates, okay, so that it can feed the wire the same rate that it can melts. Suppose if you are changing the stick out length, so obviously the system should identify any change in the voltages such a way that if there is a change in voltage means the arc length also changes. So, automatically the system should correct for it, so that no, we can do it in a constant arc length welding. So, now if you look at it, two examples I will show you, two independent parameters we are looking at it, right. So, that is the stick out length L and then the current I. The first, the effect of stick out length. So, what is the relationship between stick out length and the melting rate? If stick out length increases, melting rate also increases, okay. So, because melting rate is AI plus B L I square by pi r square. So, if L increases, melting rate increases. So, in this case everything is fixed, 1.2 mm diameter plain carbon steel, argon and 5% CO2 atmosphere. So, now the two parameters can be varied, the current and stick out length, right. So, if I change in current for a given stick out length, this is my melting rate, okay. So, this is a 20 mm extension, 20 mm stick out length, right. So, suppose if I reduce the stick out length for a given current for say 300 amperes, my stick out length is say 5 mm, in this case the melting rate will be lower than if my stick out length is say 20 mm. So, obviously, right. So, by changing the stick out length for a given current, melting rate also changes. Yes, it's clear. So, suppose if you have a 200 amperes current is used and say 5 mm stick out length, 20 mm stick out length. So, you have a melting rate or burn off rate changed from say 6.7 to 4 by changing stick out length from 20 to 5. Yes, it's clear. Very good. And then we will go to the second one. Similarly, so you can also change the melting rate by changing the diameter. What's the relationship? Inversely proportional. If you change the wire diameter, so in this case the melting rate for a 3 diameter 0.8, 1.2 and 1.6, and which will have a highest melting rate? The smallest diameter, isn't it? Say for example, for a given current say 150 amperes, which will have a lowest, what happened? The lowest melting obviously will come from 1.6 mm. So, that is the largest diameter. The maximum melting will happen for the smallest diameter, which is 0.8 mm. So, you can say changing diameter from say 0.8 to 1.6. So, you can change the melting rate from 2 to close to 8. Yes, these are experimentally observed values. Yes, it's clear. So, how the melting rate is influenced by the diameter and the stick out length. Obviously, current also has a series influence. So, if you increase in the current, obviously the melting rate also increases significantly for a given diameter, and this case stick out length is fixed when you are doing the experiment. I think 10 mm stick out length. So, diameter is changed independently to see the effect on the melting rate. Yes, it's clear. Good.